Okay, picture this. You see someone, and suddenly their eyelids start fluttering really fast, involuntarily.
Mm-hmm.
That specific kind of defining feature is called eyelid myoclonia, or EM. And for years, well, this has been the absolute cornerstone for diagnosing a specific type of epilepsy called EEM epilepsy with eyelid myoclonia. You sometimes hear it called Jeavons Syndrome, too. Welcome to the deep dive. Our whole mission here is to take a stack of information, could be the latest research, articles, notes you've sent in, and just cut through all the noise.
Yeah.
We want to pull out the most important bits, the surprising insights, and help you understand what it, really means.
Yeah.
Today we're diving into a really fascinating scientific paper. It takes a pretty critical look at how we've traditionally understood EM, and it points towards a surprising and potentially pivotal part of the brain.
That's exactly right. The paper we're digging into is titled Unmasking the Role of the Occipital Lobe in Epilepsy with Eyelid Myoclonia. It's a brief communication, but quite impactful, published in the journal Epilepsy just this year, 2025. It's by Ricci and colleagues, drawing from work mainly at the Danish Epilepsy Center and some collaborating places.
And our goal for this deep dive is to really examine this research critically. We want to understand how these findings might potentially challenge the standard definition of EM. We're zeroing in on the brain's occipital lobe, that area way at the back, the one we usually link with processing vision.
Mm-hmm.
We'll look at why these findings are important, both for diagnosis and just for our basic understanding of this condition. It's really about peeling back the layers on something that seemed pretty straightforward and discovering some unexpected complexity, and hopefully doing it in a way that makes the neuroscience kind of fun to learn about.
Exactly. So we'll first sort of ground ourselves in the established understanding of EM. Then we'll dive into the methods and, importantly, the surprising findings of this study. And finally, we'll explore the implications they discuss, which are pretty significant.
Okay, so let's rewind a bit then. Before this paper, what was the standard picture of EM or Jeavons syndrome? How is it defined?
Well, based on the criteria from the International League Against Epilepsy, the ILA-EM has long been classified as a genetic generalized epilepsy, or GGE. The thinking was that the seizure activity starts everywhere, involving both sides of the brain right from the get-go.
Generalize, okay.
Right. It typically kicks off in childhood. It's much more common in females. And like you said, the absolute hallmark is that eyelid myoclonia, the fluttering seizures, which are almost always triggered by closing the eyes.
Got it. And what else usually comes along with it?
Patients often have these very brief staring spells, what we call absences. Sometimes they happen right after or even during the eyelid fluttering. And on an EEG, the brainwave recording, you see these generalized epileptiform discharges. These are basically abnormal bursts of electrical activity spread across the whole brain. And photosensitivity, that sensitivity to flashing lights that can trigger seizures, that's also really, really common in EM.
Okay, now here's the part that this new paper really gets into, and it's like a fundamental rule in the traditional diagnosis. Historically, if a patient had focal seizures starting in one specific spot in the brain, that would actually rule out an EM diagnosis.
Exactly. The ILA criteria drew a really firm line there. There was even an international expert panel that recommended if focal seizures did show up, clinicians should probably reconsider the EM diagnosis entirely. It was meant to be a clear split, generalized, not focal.
Right, a clear boundary.
Which sets the stage perfectly for the question Ricci and colleagues were tackling. They noticed that despite this very strict rule, there had been some reports floating around, maybe anecdotal, maybe smaller studies, kind of hinting that maybe the occipital lobe, that visual area back there, does play a bigger role in EM than the traditional definition allowed for.
Oh.
So they basically asked, could focal seizures, especially ones starting in the occipital lobe, actually be happening in patients who otherwise look like classic EEM cases?
That's a pretty bold question, really challenging the established thinking. So how did they try to answer that? What was their approach?
They did a retrospective study, so they went back through medical records and, really importantly, the video EEG recordings. They looked at 21 patients who'd been diagnosed with EM at the Danish Epilepsy Center over about 5 years. And they were careful. They only included patients who definitely met the standard mandatory ILA criteria for typical EM features.
So not borderline cases. These were patients who, by the book, shouldn't have focal seizures, according to that old definition. Could you give us a quick snapshot of this group?
Sure, it was relatively small, 21 patients, but clinically very well described. Aligning with what we know about EM prevalence, the vast majority were female, 20 females, just one male.
Right.
Average age when studied was 21, but the seizures typically started much younger, around age 7 or so. Most had normal or maybe borderline intellectual function, though a few did have other things going on, like ASD or ADHD. And unfortunately, like you see in many epilepsies, most were already on multiple anti-seizure medications.
Okay, so they took this group, typical EEM, supposedly no focal seizures allowed, and did this deep dive with video EEG, recording brainwaves and video simultaneously. What did they actually find when they looked closely at that EEG data? Let's get into the results.
Well, first, they confirmed what you'd expect, right? All 21 patients showed those generalized epileptiform discharges on their EEG. Saw them when awake, saw them during sleep. That fits the definition of generalized epilepsy and EM perfectly.
Right, check. Standard stuff. But then came the twist.
Yes, and this is where it really pushes back against the traditional view. Despite EM being classified as purely generalized, they found that a huge majority, actually 90% of these patients, also had focal epileptiform discharges on their EEG recording.
90%? Wait, 90?
Ah.
That's dramatically higher than the 0% the old definition would lead you to expect.
Yeah. Absolutely. It's a striking number. And critically, they looked at where these focal discharges were popping up. They weren't just random. They were frequently found in the posterior brain regions. That squarely includes the occipital lobe.
Not back of the head.
Exactly. These posterior focal discharges were seen in 47% of the individual EEG recordings they looked at across the group. And interestingly, they were often bilateral, showing up on both sides of the back. They did see some focal discharges elsewhere too, but the posterior activity was really prominent.
So not only were focal discharges common, but they were kind of clustering right there in the occipital area.
Yeah.
Did this connect back to that key trigger for EMM closing the eyes?
Yes, and this is another really key piece of evidence linking the occipital lobe to the core EM thing. Eye closure, as we said, is the classic trigger for the eyelid myoclonia and the generalized discharges in EM.
Right.
In this study, while, yes, all patients showed generalized discharges right after eye closure, a really significant number, 76% of them showed a focal posterior discharge that consistently came just before the generalized activity on the EEG.
Whoa, okay. So it's like the abnormal electrical storm was actually starting locally in the back of the brain first, and then it quickly spread out to become generalized.
That's exactly the pattern the EEG suggested. The occipital area, or maybe nearby posterior regions, seemed to be the first place to fire off abnormally, and then that activity propagated, spreading to involve wider brain networks. The paper describes this preceding activity often as rapid spikes, or this specific fast rhythmic pattern they call spiky beta activity. It suggests very rapid, synchronized abnormal firing in that specific spot.
Okay, so seeing focal discharges before the generalized ones is one thing.
Mm-hmm.
But the traditional rule was about focal seizures. Did they actually manage to document any clear-cut focal seizures in these patients who otherwise fit the typical EEM picture?
This is probably one of the single most compelling bits of data in the whole paper. It's in their case report for patient 1. This patient had all the textbook features of EM, met all the standard criteria, everything. But, and this is crucial, during the long-term video EED monitoring they were doing, to better characterize their eyelid myoclonia and absences, they actually captured and recorded a real focal seizure.
A documented focal seizure. In someone who, by definition, shouldn't have one if they truly have EEM.
Precisely that. The seizure itself was described as having pretty subtle clinical symptoms, so not like dramatic shaking or total loss of consciousness, but maybe brief, slight changes in awareness or perception, and it was followed by amnesia, so the patient couldn't remember it. But the EEG, crystal clear. It showed the seizure activity starting in the right occipital region and then spreading forward to other brain areas.
Wow.
So having this single documented focal event in a patient with otherwise undeniable typical EM features, that's really powerful evidence against that strict exclusion rule.
That certainly punches a hole in the old rule, doesn't it?
Yeah.
Very directly.
And the authors didn't just rely on looking at the EEG traces visually. They also used quantitative EEG analysis, QEEG. This uses computer methods to analyze the brainwave data more objectively.
Okay, the computational stuff.
Yeah, things like spectral analysis to look at the power of different brain rhythms, amplitude mapping to see where the activity is strongest on the scalp, and source analysis, which uses algorithms to estimate where the activity is likely coming from, deeper inside the brain.
And did that back up what they saw visually?
It absolutely did. This objective data reinforced the visual findings. The quantitative analysis supported the idea that the occipital, or at least the posterior region, was heavily involved. It often seemed to be the starting point, or at least showed the highest level of activity related to those eye closure events and the generalized discharges in most patients. I think it was 86% showed evidence of posterior onset or prevalence in the amplitude maps. And the source analysis specifically pointed to a predominant occipital representation for the generalized spikes they saw.
Okay, let's take a step back and think about what this all means.
Yeah.
You've got frequent focal posterior activity. You've got this pattern where it precedes the generalized discharges, and you even have documented focal occipital seizures in patients who otherwise have textbook EEM. How do the authors pull all this together? What's their big interpretation?
Well, their main takeaway is that this data strongly points to a pivotal, maybe even primary role for the occipital lobe in how EM actually works, the underlying mechanism. It's not just, passively affected by some generalized discharge starting elsewhere.
Hmm.
They're suggesting the occipital lobe, or perhaps a network centered right there, acts as an epileptic generator. It kind of kicks off the abnormal electrical activity, which then spreads out to engage broader brain networks, including the ones we typically associate with generalized seizures.
So the occipital lobe isn't just part of the problem in EM. It might actually be the source of the problem in many, maybe most cases.
That's the compelling argument they're making, and it's backed up by both the visual and the quantitative EEG findings. They also try to connect this idea to features we already know are common in EEM. The occipital lobe's job in vision, well, that obviously links to photosensitivity, right? That light sensitivity, so typical of EEM.
Makes sense.
It might also tie into problems with the brain's alpha rhythm system, which is really important for visual processing and attention, and we know that can be altered in photosensitive epilepsies. And probably other brain areas involved in controlling eye movements are part of this network too.
Okay, so if the occipital lobe is so fundamentally involved, it kind of inevitably brings up a question that's been kicked around for a while. Are EEM and other occipital epilepsies related? Maybe even the same thing. I'm thinking specifically of photosensitive occipital lobe epilepsy, or POE.
Yeah, that's definitely been a long-standing discussion point. Because they share features like occipital involvement and photosensitivity, people have wondered, is EM just a type of PLE or maybe the other way around?
And what do Ricci and colleagues say about that relationship? Are they arguing that EEM is actually POL based on their findings?
No, interestingly, they argue against just lumping the two together. They point out that under the current ILA classification system, EM and POL are still considered distinct syndromes. Why? Because they tend to have different overall clinical pictures, maybe different impacts on cognition, and often different long-term outcomes or prognosis.
Oh, okay.
So they believe it's still important to keep these distinctions based on how the conditions usually manifest and evolve over time.
Okay, so they're not saying EM and POL are identical, but their findings show this really strong overlap in where the trouble seems to be starting, in that occipital region. How do they square that circle of distinct syndromes, but a shared origin point?
This is where they introduce a really interesting concept, which they call system epilepsy. Their proposal is that maybe EM and POL aren't identical syndromes, sure, but maybe they represent different clinical expressions, or perhaps they lie on a kind of phenotypic spectrum. And the spectrum arises from dysfunction within a shared underlying neural network that crucially includes the occipital lobe.
Ah, okay, so like think of the brain as this complex network of roads. You could have different kinds of problems on the same major highway, this occipital network, and depending on exactly how and where that network is disrupted, you might get different kinds of traffic jams or symptoms that we recognize clinically as either EM or POL, but they stem from the same basic faulty infrastructure.
That's a great analogy, yeah. The occipital lobe is like a critical hub in that faulty network, and then the problem within that network plays out clinically, leads to either the EM picture or the POL picture, even though the underlying mechanism might be starting in the same general brain area.
And why is this shift in thinking moving from seeing EM as purely generalized to understanding it has this strong, maybe initiating focal occipital part? Why is that so critical? What's the practical impact for doctors managing patients?
Oh, it's hugely practical, especially for clinical care. The authors really stress that focal seizures in patients with EM are probably significantly underestimated. Remember, patient one's documented focal seizure.
Yeah, subtle symptoms, then amnesia.
Exactly. If a doctor isn't actively looking for those subtle focal signs, or maybe if they're still working under the old assumption that EEM patients just don't have focal seizures based on the traditional criteria, well, they're going to miss them completely.
And missing focal seizures means you might not fully understand the patient's epilepsy. And maybe you're not treating it as effectively as you could be, right?
Precisely. If a patient is having these unrecognized focal seizures happening alongside their more obvious generalized events, the treatment strategy might need tweaking. You might need therapies that specifically target that focal activity starting in the occipital network, in addition to managing the generalized stuff.
So what's the call to action here? What do the authors recommend based on all this?
Their main recommendations are basically two things. First, they argue for more extensive, longer video EEG monitoring in patients who get an EM diagnosis. Longer recordings just increase your chances of catching those less frequent or more subtle events, including potential focal seizures.
Makes sense. More time, more chance to see everything.
Right. And second, and this is perhaps the biggest point, they suggest that the traditional ILA exclusion criterion for EM, that rule saying focal seizures mean it can't be EM well, that rule may need to be formally reconsidered based on this growing evidence showing focal involvement is actually common.
That's a pretty significant step, potentially changing the actual definition of a recognized epilepsy syndrome. It really underlines how important it is for research to keep challenging even established ideas.
It really does. And this research, it isn't just some academic exercise. It has direct implications for day-to-day clinical practice. It could lead to more accurate diagnoses, a better understanding of what's really going on in an individual patient's epilepsy, and hopefully more effective treatment strategies for people living with EE.
So this deep dive into the Ricci paper really does unmask a surprising and much more complex picture of epilepsy with eyelid myoclonia. Those classic generalized eyelid flutters, the condition likely has this strong, maybe even initiating root deep in the occipital lobe. And those subtle focal occipital seizures and the frequent focal discharges they found, they seem to be much, much more common than the traditional definitions ever really allowed for. It directly challenges those existing diagnostic criteria.
Yeah, and what's really fascinating, I think, is how studying what seems like a very specific epilepsy syndrome can actually unlock deeper insights into the basic mechanisms of how seizure networks work, maybe even across different conditions. It forces us to think a bit beyond these rigid syndrome boxes and consider the interconnected brain circuits that are actually driving the activity.